Using Table E in Appendix A, find the critical values for each situation and draw the appropriate figure showing the critical region. So Part A says we have a left-tailed test with alpha equal to 0.10. So Part A, alpha is equal to 0.10. And we have a left-tailed test. A left-tailed test means that our rejection region is down here to the left. Our hypothesized parameter, or our assumed parameter, would be right here in the middle. It could be a test about a mean or a proportion, it doesn't matter. The z-value here would be 0. What I'm doing here is establishing a critical value, and that critical value will be a z-value. We'll call it the z-critical value. We're told that alpha is 0.10, and what that means is that the area in the rejection region is 0.10. Let's write that down. Since alpha is equal to 0.10, the area in the rejection region will be 0.10. So that means that this area right here is 0.10. That also means that this area here from this critical value up through is 0.90, since the total area will be 1. Or another way to say that is 90% of the distribution will be above this critical value and 10% will be below. Let's remember how our standard normal distribution table is put together. Along this far left column, we have our z-values out to tenths place. Notice these are negative. Looking at the picture at the bottom of this table, we see this shaded area down here. That area corresponds to these probability values inside the body of the table. And to the left of the mean, the z-values are negative. That's why we have negative z-values here along the far left column. And then across the top, we have the hundredths place value. Now remember that this shaded area right here is the same as this area that we have here in our drawing. And here we have then a place where 10% of the entire distribution has accumulated to that point. And that's what these areas in the table represent, that accumulated area. So we want to find somewhere in this table where 10% of the whole distribution has accumulated. So as we look through here, we find 0.0985 in this entry, and that is at minus 1.29. And then next to that, we find 0.1003 at minus 1.28. Now, minus 0.0985 is 15 ten-thousandths less than 0.1. 0.1003 is 3 ten-thousandths greater than 0.1. So since this value is closer, we're going to select minus 1.28 as our critical z-value. Again, that means that's the point where 10% of the area has accumulated. So this value will be minus 1.28. In Part A of Example 2, we are to find the critical value associated with a left-tailed test where alpha is equal to 0.10. And let's notice what happens with a left-tailed test when alpha is 0.10. This shaded region here, then the rejection region, would have an area of 0.1. That means that the rest of the distribution from this critical value on up would be 0.90. Or in other words, 10% of the distribution would be represented by this shaded area, and 90% would be the remainder from the critical value on up. We can use the TI-83 or 84 calculator to find that critical value. We'll do that by pressing second, variables distributions, then going to 3 for inverse normal. That accumulated area was 0.1. We'll leave the mean at 0 and the standard deviation at 1 since we are finding that z value that is associated with a standardized normal distribution. Then we'll go down to paste and hit enter. If you're using a TI-83 or 84 calculator that does not use those menus to prompt for the values, then the order that you will enter these values in will be the accumulated area, 0.1, comma, the mean for the standardized distribution, which is 0, comma, the standard deviation for the standardized normal distribution, which is 1. Close your parenthesis and hit enter. This will give you the value of minus 1.28, this critical value, negative z value, which is to the left of the mean. And here we see it's minus 1.28, the z value associated with this point where 10% of the distribution is to the left and 90% is to the right.